Hi, I'm Chad Burrows and thank you for watching my YouTube channel, where I share Lean Six Sigma tips, tools, and information I've learned over the past 22 years of my career. I remember the first time I actually heard the term Six Sigma, I actually had no idea what the term meant other than it was great to have a Six Sigma process, but I didn't truly understand and appreciate what Six Sigma actually is. Once I was attending this leadership training class in New York, the organization that was hosting the training class had this great little library. So during one of the coffee breaks, I decided to take a stroll down to the library. And they had this small section of Lean Six Sigma books, so naturally I gravitated there. Now, while in that section, I saw a couple of gentlemen from the training class, and I overheard one of the gentlemen say to the other gentleman, "Why do they even write books on Lean Six Sigma? I mean, I can sum the whole book up for you right now. Six Sigma means 6 defects per million opportunities. That's what the whole book is about." Well, it was obvious this gentleman was just like me. He didn't really understand what the term meant either. And I've come to realize that this term can be difficult to understand. So today in this video, we're going to dissect the term Six Sigma and find out what's on the inside. Okay, so the American Society of Quality, or ASQ, defines Six Sigma as a methodology that provides businesses with the tools to improve the capability of their business processes. This increase in performance and decrease in process variation lead to defect reduction and improvements in profits, employee morale, and quality of product. And at its core, that's exactly what Six Sigma is all about. Well, that and achieving a quality level of 3.4 defects per million opportunities, not 6 defects per million opportunities as the gentleman in my training class thought. And still, that's a great definition, right? But it doesn't break down exactly what the term Six Sigma is. So let's keep dissecting this ourselves. So this is what Six Sigma looks like. We have a 6 and we have a sigma. Now, we know what 6 is, right? It's just a number on the number line. So let's talk about the part that's a bit more mysterious, the sigma. Sigma is the 18th letter of the Greek alphabet and translates to S in the English alphabet. The uppercase sigma refers to the summation or mathematical sum. But the sigma we're concerned with is the lowercase s. The lowercase sigma means standard deviation. So if we combine the number 6 from Six Sigma and replace sigma with the definition we just learned for sigma, we get 6 standard deviations. Okay, now we're getting somewhere. So when we hear the term Six Sigma, we now know that we're really hearing 6 standard deviations. But what exactly is a standard deviation? Let's keep dissecting. Now before we go on, let's look at the standard deviation formula. Now it might look a little intimidating, but most things do until they're understood, right? So let's break this formula down together. In mathematics, there is a rule called order of operations, right? We always do what's in the parentheses first. So let's first look at what's inside the parentheses. We have x minus an x with a bar over it. The x represents the individual values or data points. The x bar rather, represents the average or mean of the individual data points. So we're supposed to subtract the individual data points from the mean. Then we square the individual data points as indicated by the little superscripted 2 there. The capital sigma that looks sort of like an E is instructing us to sum up the individual squared results. Now we divide that result by the number of data points we have. This is represented by n. Once we have that value, we take the square root and we finally have our standard deviation. Don't worry, we'll cover and work an example later together. For now, let's just keep dissecting. Now at a fundamental level, standard deviation is variation, but can be more accurately defined as the average distance from the central location you expect to observe. A great way to illustrate the standard deviation of a process is with a histogram. A histogram is just a graphical representation of a set of data where the columns represent the frequency of occurrences. Histograms make it easy to see the dispersion and central tendency of our data. So now we know that sigma means standard deviation and deviation is just variation, but what exactly is the standard deviation measured against? For example, if we're measuring something like the temperature of food and we want to know exactly what temperature provides the best taste, well, if we just collect the temperatures and measure the standard deviation, all we'll know is how much the food temperatures vary around the mean or average of that data set. And that's somewhat helpful, but certainly won't tell us which temperature is best for taste. It will just show us how stretched or squeezed the data set is. But what about the 6 from the Six Sigma? Right? We can't forget about that 6. It's a very important number, right? 6 standard deviations must mean that we're measuring 6 standard deviations from something to something, right? And in fact, that's exactly what it means. Six Sigma requires that processes operate so that the nearest requirement, usually specifications set by the customer, is at least 6 standard deviations from the process mean. Let's work an example together to clarify these concepts. So let's pretend we've been hired by a hotel chain to determine why they've been getting bad reviews on their food service. Now, we've done our due diligence and we found out that in-room dining food temperature are what's causing all the bad reviews. This histogram represents the data we've gathered. Specifically, it represents the temperature of hot food when delivered as part of the hotel's in-room dining service. We've determined from customer feedback that our hot food tastes best when it arrives to the room heated between 130 degrees and 135 degrees Fahrenheit. If the temperature is 136 degrees Fahrenheit, it is too hot. If it's 129 degrees, it's too cold. So 130 and 135 degrees Fahrenheit become our specification limits, or are represented by the 2 lines on the histogram. Remember, these are our customer specifications. These are known as the lower specification limit and the upper specification limit. Now, as stated earlier, for a process to be a Six Sigma process, it must demonstrate that it can operate so that the data set average, or mean, is 6 standard deviations away from the nearest specification limit. Let's quickly calculate the standard deviation of our food temperature. Remember that standard deviation formula we had? Let's go through that. So step 1, we document the actual temperatures of the food. This is the data we've collected. Next, step 2, we calculate the average of the food temperatures by adding these values together and then dividing the result by the number of values, which in this example is 10. Now for step 3, we take the individual temperatures and we subtract the average. It's okay to have negative values here. You can see that we've taken the first value of 132.45 and subtracted the average of 133.28. And this gave us a result of a negative value, which was negative 0.83. Now keep subtracting each individual data point from the average or mean. And step 4, we square the results from step 3. We'll do this for each individual data point. As you can see, I've already done that here. The next step, step 5, we simply add up all the squares from step 4 and we get 2.77. Now, step 6, we divide this number by the number of individual data points. For this example, that would be 10 because we have 10 data points. So 2.77 divided by 10 equals 0.277. For step 7, we take the square root of our step 6 result and we get a value of 0.53. And 0.53 is our standard deviation. This number tells us that our data, hot food temperatures for our example, has an average deviation distance of 0.53 degrees from the mean. Look at this on the histogram. Here I've gone ahead and put the standard deviations on the histogram. We've discovered our standard deviation to be 0.53. Now if we add 0.53 to the average of 133.28, we get a sum of 133.81. 133.81 is one standard deviation from the average. If we continue to do this, you can quickly see that 134.87 degrees, we've almost reached our customer's upper specification limit. In fact, if we go one more standard deviation, we get 135.4 degrees, which exceeds our customer specification. We can only fit 3 standard deviations between our average and the nearest customer specification limit. Now, for the sake of showing you 6 standard deviations, let's take a look at the other side of the average. We can see that we are 6 standard deviations from the average to the lower specification limit. If both sides of the average demonstrated this, we could say that we had a Six Sigma process. But as it stands, the hotel will want to make some adjustments to their food preparation process if they want to consistently deliver food that arrives heated between 130 degrees and 135 degrees Fahrenheit. So now when you hear someone say we're operating at a Six Sigma level, I hope you have a clear understanding of what Six Sigma is all about. It's not 6 defects per million opportunities, it's actually 3.4 defects per million opportunities. And Six Sigma is all about the mean and the specification limits. How many sigmas can you fit between the data, mean, and the specification limits determines exactly what sigma level you're operating. Hey, I want to thank you for watching this video. I sincerely appreciate your support, truly. If you like this video, please click the like button below. Feel free to share it with a friend or colleague who might get value from it. And don't forget to click on the subscribe button below, because I'll be providing data like this or information like this weekly, and I don't want you to miss that. I'm Chad Burrows, and I will see you in the next video.